the processor invented by the Intel Corporation, which is a 4-bit microprocessor, which is numbered as 4004, and it was used 2300 transistors in a single chip, and its speed was very much low, 108 kilohertz only, and address bus is only 10-bit. Later, in 1972, again, they developed a 8-bit microprocessor, 8008, in 1972, which is embedded 3500 transistors only. And the speed of the clock is very much low, that to 200 kilohertz, and which is address buses of 14-bit and data buses of 8-bit. And then in 1974 and 76, the 8080 and 8085 was made by the Intel Corporation, and which is almost double the transistors are embedded in a single chip. The frequency of oscillation, the clock speed also increased to 5 megahertz, and which is address buses of 16-bit and data buses of 8-bit. And we can address the memory of 64 kilobytes of memory. And then 8086, which is of 16-bit address processor and 20-bit address bus, and it is enhanced to 1 mega bytes of memory it could address. And in 79, the 8088 was made by the Intel Corporation. The transistors were 29,000, and clock speed is 5 megahertz, and which is also a address bus of 20-bit and 16-bit of data bus, and it could address 1 megabytes. So in 1982, 80286 was made by the Intel Corporation, which is the clock speed is of 8 megahertz, and address bus is of 24 bits, and data bus is 16-bit, and it could address 16 megabytes of address. Is much more increased it, and 80386 in 85, and it is a initial clock speed of 16 megahertz, and which is a 32-bit address bus and 32-bit of data bus, and it's 4 gigabytes of memory, which is very high speed. And in 99, 8046 was made by Intel Corporation, and transfer was 1.2 million, and the clock speed is 25 megahertz, and which is also a 32-bit microprocessor. Data bus is of 32 and also 64-bit, and data bus address bus is of 32-bit, and the address memory is 4 gigabytes of memory. Then 80486 after that, then Pentium was made, which is 1993, and which is 3.1 million transistors and 32-bit address bus, and 64 and 32-bit data bus, which is of memory of 4 gigabytes. And Pentium Pro in 95, Pentium 2 in 97, Pentium 3 in 1999, and Pentium 4 in 2000, and the data bus is of 64, and the memory also 64 gigabytes, and memory that we can address. Now, coming to the 8085, which is a microprocessor or central processing unit. In any computer system, we have a memory, and that is EPROMs. Yesterday, what we discussed is about EPROMs and ROMs, and then some of the IO devices. This particular picture shows you about the microcomputer, which is address bus and data bus is connected, and some of the control signals are also connected. Data bus is of bidirectional, where the address bus is a unidirectional. So the processor 8085 is completely of consisting of all these devices. One is a microprocessor and the memories, peripheral devices, and some of the buffers, and control lines which are connected. Then, looking at the pinout diagram of 8085, this 8085 is a 40-pin device dual in package, which runs with plus 5 volts and ground, which is pin number 40 is considered as VCC, and pin number 20 as ground, and the crystal is connected X1, X2. This crystal is of 3.072 megahertz and and it can 6.144 megahertz of crystal is connected to pin number 1 and 2, and this clock is generated is 3.072 megahertz. Clock is generated from this crystal and then reset out is pin number 3. This is to reset all the other peripherals which are connected to the microprocessor. Reset out is connected, and we can reset all the other devices whenever it is required. And then SOD and SID, these are the serial output data and serial input data. Serially, we can send data or receive data through these pins. We can receive data from SID and directly it is entered into the microprocessor. In the microprocessor, we have a 8-bit accumulator is connected, is there. The data directly enters into the accumulator, and whenever we want, send serially the data from the accumulator to the output device through a serial pin, which is SOD. So accumulator to this SOD, we can send out the data. Then these two comes under the serial data input and output. And then this pin number 6 to pin number 11, these are the interrupt pins, which is trap, RST 7.5, RST 6.5, RST 5.5, INTR. These are the interrupt pins of 8085. And whenever there is a servicing is required by any of the devices, the processor sends, the processor receives the interrupt request so that the servicing takes place. After receiving any of the interrupt, the processor sends one interrupt acknowledge signal, and then the servicing takes place according to the priorities. The first priority is given to the trap, then priority is 7.5, then priority is given to 6.5, then RST 5.5, and then it is 6 INTR. So this is the level of priority. So the trap is given highest priority, and it's a non-maskable interrupt. So the processor gives the most priority to the trap, where the others are lateral priorities. And then whenever it receives the interrupt, then immediately the processor, if it is ready, then it sends acknowledge signal, and then according to the priority, the service takes place. Then coming to pin number 12 to 19, this is the lower order address, and pin number 21 to 29, 28, this is the total address bus and data bus, where in the processor, to save some of the pins, the address, lower order addresses and data bus is connected the multiplexer. So whenever we want the address bus or whenever we want the data bus, we can demultiplex using the address latch enable signal. So if this is activated, then address and data will be separated. So we can save 8 pins of the 8085 so that data will be received or sent through these 8 pins only. Whereas the higher order address from 21 to 28, these 8 pins are called higher order address, and this is not multiplexer, and it is connected directly to the devices where it is required. And address bus is a, once again I repeat, address bus is a unidirectional and data bus is a bidirectional. Then 29, pin number 29 is address latch, and this is a status pin. So S0, S1, 33 and 29 are meant for the status, to know the status. This will be discussed in the next slides. S0 and S1 are the, what is the doing at that particular moment was S0 and S1, 0, 0, 0, 1, 1, 0, and 1, 1. Basing on this particular, looking at these two pins, we can find out what actually the processor is doing. Then 30, pin number 30 is the address latch enable signal, which to demultiplex the lower order address and data bus, we can use this address latch enabled signal. Then coming to the pin number 31 and 32 and then 34, these three are read, write, and IO by M bar. So this is active low. Whenever the pin number 31 is low, it is writing, is active, and 32 it is reading, which is when it is low, it is active. Then IO by M bar. So in pin number 34 is IO, if it is 1, then it is refers to IO device. When this is low, then it is memory is related. So all these three are generated again, IO read, IO write, memory read, memory write. So all these, out of these three, we could get the four various pins. So this is whenever you want to send data to the memory, then memory write signal to be activated. When you want to get the data from the memory, so memory read signal has to be activated. Then if you want to send some data to the IO device, then IO write will be activated, and then IO read. So to get the data from the IO device, this IO read signal should be sent along with the data and address bus, so that all the information that we can access from the IO device or the memory. And these three are the very important pins of the 8085. Then coming to the pin number 34, this pin number 34 is a ready signal which is used in the wait states. So whenever you want to transfer data from higher speed and lower speed processors, then whenever a higher speed processor is um, ready, then the data transfer takes place. So the speed, higher speed processor should be in the wait state, so that whenever the data, the speeds of the processors are equal, then data transfer takes place. Till that time, it will be in the ready state or wait states. Then reset in. So to reset the processor in the data inside, then this is an active low pin, reset in will be activated. Then we have a clock out, then the same clock 3.072 megahertz is a clock connected to other peripherals. We can make use the clock out signal. And coming to 38 and 39, this is the hold signal, which is in the use of the DMA operation. This DMA operation, that is direct memory access, whenever the data transfer from IO to memory or memory to IO or memory to memory or IO to IO. So during this particular transfer of the data, the microprocessor will receives a hold signal from the device DMA, and then sends an acknowledge signal HLDA. Then it handovers the address and data bus to the DMA so that the data transfer takes place by the DMA, and it relinquishes all the uh, information, the signals, then hand over the address and data bus to the DMA. The DMA transfers from memory to memory, or memory to IO, or IO to IO, or IO to IO device, so that the data transfer takes place. So to summarize this, these two pins are crystals. Crystals are connected to X1, X2, reset out to reset the other pins. SOD, SID are the serial data input and output. Then 6 to 11 pins are interrupt pins. 12 to 20 and 19. This is the lower address and data bus, a multiplexer one, and 21 to 28. This is the higher address which is connected to the processor, and status S0, S1 are the status signals to fetch cycle or read cycle, or what is the status that we can understand. Read bar, write bar, and IO by M bar. These three signals generate control signals as generated, and will be used in data transfer, not data transfer to the memory, or IO. Read or write, get the data and send the information, and clock input, and then DMA operation hold and hold acknowledge. So this is all about the pin diagrams of 8085, and it can address 64 kilobytes of memory and requires 5 volts power supply, and this is what. Then coming to the signals can be classified, which is address bus, lower address, data bus, and what are the input pins and output pins. It is showing in this diagram. Extensiated signals and serial IO ports. So this is the pins that are connected. So this is also an important diagram to remember. This is the internal diagram of the 8085. In the internal diagram, the sections, interrupt section, and we have serial IO control system, control part of it, and it has an accumulator inside, temporary registers, instruction registers, multiplexers, and there is a timing and control unit. All the pins that are connected, control signals are connected to this timing and control unit. And we have address bus and also address and data bus. There's lower address bus and data bus, and the higher address bus. So looking at the internal diagram, if you understand properly this particular diagram, we can program the microprocessor very well. So what happens when data is, the program is written, so that immediately the instruction register receives the information. So we write the program in the assembly language program, and the assembly language program, again, it is having some opcodes. So each instruction will have an opcode. That opcode is of 16 hexadecimal number. That hexadecimal number is again converted into machine language, that is zeros and ones, and the instruction register receives the information that the instruction decoder decodes, and it will be generated what type of signals that has to be required to send out or receive the signal. So once the instruction decoder is received the signal, then again the data will be, next data will be received, and some of the registers are temporary, it will be stored in the temporary registers. Like here is one 8-bit data, and you have a temporary register of W and temporary register Z. Then we have a register accumulator. This accumulator is of 8-bit. So all the arithmetic and logic and operations and will be done using the accumulator only. And B, C, D, E, and H, L, all these six and including this seven are available to the programmer. We can program basing on these data. Um, the capacity, we have 8-bit capacity, and this is also 8-bit, and this is also 8-bit. D and E and H and L each are 8-bit, and if you want to send the data 16-bit, so BC is of one pair, so we can send the data of 16-bit data, and D is one pair, and HL is one pair. So if 16-bit data of three sets we can send data, whereas accumulator is only a 8-bit data. So once the instructions are, the program is understood, so in detail we can understand this. So coming to the again the accumulator part, and this is discussed. Then the instruction register receives instruction and decodes it, and generates the required timing and control signals to send out or receive data. And then it also have one arithmetic and logic unit that is connected with the accumulator and temporal register. So all the arithmetic operation, logical operations will be done in the arithmetic and logic unit, and is also connected a flag register. This flag register is of 8-bit, but we have only 5 flags are there. So which is though it is 8-bit, so we have only 5 flags will be there. So we'll discuss this in the next slide, coming slide. So this part is this. Then coming to the stack pointer. So the stack pointer is used in the case some of uh, the address of this, it is mentioned when we write a subroutine programs, the data uh, which is there till that main program in subroutine, it will be stored in the stack pointer, which is mentioned in this some portion area of the total memory. So some portion is allocated for the stack pointer, so this data will be stored in the stack pointer, and then after completing the subroutine program, again it will be retrieved from the stack pointer, and it will be restored with the main data of the main program. So during subroutines, the main data will be stored, and after completing the subroutine, again data will be retrieved from the subroutine, the stack pointer, then it continues the main programming part. So during this, the stack pointer address to be mentioned in this case. So that is a stack pointer. That the program counter is a which stores the address of the instruction to be executed in the next cycle. The program counter will be stored in that address of the, and then increment and decrement address latch. So it will be ready to send the address to, so that the generating this address is sent to the memory and gets the data of the memory and place it wherever it is required. And again, in the next address, again, next address will be sent to the memory, and then the next address, next data will be then retrieved from the memory and then keeps in the uh, instruction register, and it process it. So this is how it continuously continues the uh, mm, data retrieving from the memory and process it and executes it and then send back to the memory, and it continues. So all these pins which are discussed in the pin diagram are seen here. X1, X2 are the clock and clock generation, clock out, ready, read bar, write bar, A, B, status bars, status S0, S1, IO by M bar, hold and hold acknowledge the DMA operation, and then reset in and reset out are the pins. So this is the internal block diagram or internal diagram in the case of in architecture of 8085. So this is our how the operations get performed with the data operations. Stores 8-bit data, perform arithmetic and logic operations, test our conditions, sequence the execution of instructions, store data temporarily in read and write memory called stack. Then 16 signals use of address bus. This is what discussed in the last slides. A7 to AD0 and no lower address, and to execute instruction early in AD7 to AD0, yes, address bus, and after TS data bus for next cycle. And bus multiplexing method to change address bus to data bus is known as multiplexing, and demultiplex using the ALE. So these are the control lines, two control lines, RD bar and write bar, read bar and write bar, and three status signals, IO by M bar and S0 and S0. One special signal as ALE to demultiplex, read bar and lower address and the data bus. So this is the indicate the IO or memory selected to be read data in available. This is what we discussed. This is also active low, indicates that data available in the bus are to be written to memory or IO ports. To differentiate IO operation or memory operations, 0 indicates memory operation because IO by M bar is written. So for 0 it is active, memory is active, and IO is 1. 1 is indicates IO operation. So IO by M bar combined with R bar, read and control signals. Yeah, now coming to this, the status of this, what actually is happening. So if the both signals are was 1, and this is 0, then it refers to the memory. So during this, it is read bar is 0, then opcode fetch will be done when S0 and S1 is both are 1. Opcode is means whenever you write a software program, each instruction will have one hexadecimal number, which is called opcode. So that opcode will be getting by sending address bus by the processor, and it receives from the memory. So during this, the opcode fetch will be taking place. Then the next part is the memory read. So by sending the address and read signal, the processor reads from the memory device and retrieves. Then memory write. So this is IO by M bar is 0. So that the and S0, S1 is 1 and S0 is 1. S1 is 0 and S1 is 1. Then whatever the data that is there in the processor, that will be in the memory, it is written in the memory. So this refers to M bar is 0 and S0 is 1 and S1 is 0. Then it is a memory write takes place. Then similarly, if IO by M bar is 1 in these three cases, so the first case is IO read. So it refers to the IO device 10, which is reading takes place, and IO write is 1 is connected, so that it is refers to IO, and then S0 and S1 is 0 and 1. Then writing takes place. Then if both all the three are 1, then interrupt acknowledgement is active. So it is sending the interrupt acknowledge signal, and this is not mentioned here. Both are 0. Then halt takes place during hold takes place in XX and it is Z. So it is a tri-state and is unspecified. So during the tri-state mode, and it is unspecified. So this is how we can, by putting our checking at these 2 pins or 3 pins, we can find out at any point of time, we can find out what actually the processor is doing. Then this is demultiplexing of the ALE, demultiplexing of the address bus and data bus. So whenever there is a latch is connected here, this latch is of 8-bit. So the center one is connected to the ALE. Whenever the signal is active, then it acts as a data address bus. Otherwise, it is continuously acts as a data bus. So this is address latch enabled signal operation. Then the power supply and the crystal is connected at 6.072. 6.144 is the actual correct exactly the value of the crystal, which is connected to the processor, and the clock out is 3.072. Then again the interrupt request. This is used to general purpose interrupt, similar to the INT signal of 800. Once it receives the interrupt request, the processor sends an acknowledge signal. This is used to acknowledge an interrupt. And interrupts are again three different interrupts are there: RST 5.5, 6.5, 7.5, are vector interrupt and transfer the program control to specific memory locations. They have higher priorities than the INTR interrupt. Among these three, the highest priority is given to 7.5, then 6.5, and then it is 5.5. And the next one, that is fourth and the fifth one, is the trap. This is non-maskable interrupt and has highest priority. So this is what we discussed in the last few minutes back. And then hold and hold acknowledge indicate the peripherals as DMA data memory access control is requesting the use of address and data buses. Once it receives the hold signal, the processor sends hold acknowledge signal. Then coming to the ready signal, this signal is used to delay the processor read and write cycles until a slow responding peripheral is ready to send or accept the data. When the signal goes slow, the microprocessor waits for its integral number of clock cycles until it goes high. So whenever the data transfer is required from a lower speed peripheral to the processor, then it will be the wait states, and then this data transfer takes place. Yeah, interrupt hardware initial subroutine call. Interrupt is activated. ASR will be called interrupting the program that is currently executing. Subroutine locations are here, it is mentioned. Input is enabled when interrupt enabled instruction is executed. So that status we can program these status interrupt enabled instruction and condition of the mask bits in the interrupt register. This is about resetting. If you want to reset, if you push this button, then the reset of the 8085 will be reset out, and reset output is connected to all the peripherals is used to reset other devices. We can use this. Yeah, this is also discussed as serial input data and serial output data. And the lower address bus is multiple data bus, demultiplexed. Yeah, this is again how the out of these three, how these four signals are generated. This is for all these are available in a chip form. And IO by M bar, read bar, write bar is connected to these three inputs. Then it would be generated memory read, memory write, IO read, and IO write. So to read from the memory, the data processor sends it makes it active, so that memory signal will be sent to the memory and gets the data in the data bus and keeps in the data bus, and then processor seed set. Then if you want to store from the processor to the memory, so the data will be placed in the data bus, and the memory write signal is generated, and address also will be sent where the data will be stored in the memory. The address is specified, so in that particular address, data will be stored. Then if you want to get the send data or receive data from the IO device, this IO read signal will be active. So this control signal plus the data bus will be sent, and address bus also will be sent, so that wherever the data is available, then it sends to the IO. Then IO data will be placed in the data bus and will be read by the processor. Similarly, if you want to send some data to the IO device, then the processor sends address and data in the data bus, and IO read controls is also sent to that, and then the processor sends the data information from this data bus to the IO device. So this is the most important part in generating the data transfer, which is from the memory or to the processor, or memory to processor, and IO to processor, or processor to IO, and so on. This is again demultiplexing is clearly indicating how the lower data bus or address bus is demultiplexed. So this is the D flip-flop is connected here. So whenever these are basically it's a tri-state buffer, whenever this enable signal is active, then D will be transferred to this tri-state, then you will get the address here. So like this, we have 8 D flip-flops are there, and 8 tri-state buffers also connected here. This is a complete picture how the connected to this demultiplexer and generated 4 generated signals. Yeah, this is the communication, how it takes place. It will be so. This is reading means whatever is the data is placed in the memory. That is these are the addresses of the memory, and this is the data. So in the address 2005, there is a data 4F that has to be read by the processor. So what happens is the program counter sends the address of the where the data is there. So the process sends the address of the uh, address where the data is available. So it will be sent to the memory chip, and at the same time the control signal also sent as memory read signal is also connected to this chip, so that once it receives the signal, the whatever is the data which will be placed in the data bus, and the data bus receives and then takes to the internal data bus and keeps it, and instruction decoder decodes what is by meant by 4F. So this is how a address is sent by the processor, and the memory puts the data, corresponding data in the data bus, and data will be placed in the internal data bus, and the instruction decoder will take care of the data to be processed. So this is the instruction move C, A. It means the contents of A are moved to C. The microprocessor plays a 16-bit memory address from PC. We have address 20 and 15, 8, and lower address is 05. So here is active high synchronously. IO bar is active low condition to show it is a memory operation. Then active low control signal. Read bar is activated so as to activate the read operation. It indicates that MPU is in the fetch mode. The active low read signal enable the byte instruction 4F to be placed in the 87 to 87 and transferred to the MPU. While read is high, the data bus will be high impedance mode. So it means once the process is over, once it is active, then it will be low, then it is active. When the process is completed, then it will become high. So the machine code 4F will then be recorded in the instruction decoder. The content of the accumulator will then copy it into C register. Then the ALU, arithmetic and logic unit, and the timing and control unit, instruction register decoder, register array, interrupt controller, and IO control. This again a general purpose registers to store 8-bit data during the program. This is what I'll discussing the internal diagram. We have discussed this B, C, D, E, H, L. These are the 6 general purpose registers, and this B, C, D, E, H, L. They can be combined as a register pairs B, C, D, E, H, L to perform some 16-bit operations. These registers are programmable. It can use to load or transfer data from the registers by using instructions. And apart from this 6, we have one more instruction register called accumulator. This is also a 8-bit register, and it's a part of arithmetic and logic unit. And this also use all the operations will be done, arithmetic and logic operations. The result of an operation is stored in once the addition or subtraction or any operation, again the information will be there in the accumulator itself only. And this is identified as register A, data on which the register operations is to be performed is operand. The operand is be an accumulator. And the program counter 6 deals with the sequence of the execution of the instructions. The memory pointer, memory locations have 16-bit address. Uses this register to sequence the execution of the instructions. The function of counter is to point to the memory address from which the next byte is to be fetched. It stores the address of the instruction to be executed in the next cycle. When a byte is being fetched, the program is automatically incremented by 1 to point to the next memory location. So this will be stored in, this will be sent ready with the next address location. Stack pointer is also a 16-bit used in a memory pointer. It memory location read-write memory called stack. Beginning of the stack is identified by loading 16-bit address. Timing and control unit. It synchronizes all the microprocessor operations with the clock and generates a control signal necessary for communication between the microprocessor and the control signals are similar to a sync pulse in an oscilloscope. Read bar and write bar signals are sync pulses indicating availability of the data. So in the internal diagram of 8085, we have instruction register and a decoder as part of the ALU. Is fetched from memory. It is loaded into the instruction register. The decoder decodes instruction and establishes a sequence of events to follow. So what actually the programmer is planning, that will be mentioned in the program. So that is understood one by one, fetched by the from the memory, and decodes it and then establishes a sequence of events. The instruction register is not programmable and controlled to be accessed by the any instruction register array. This is what we have seen. B, C, D, E, H, L, stack pointer, and program counter are used to hold 8-bit data during the execution of the instruction. However, they are used internally by microprocessor. They are available to the programmer. Unit is to select registers out of which available register. Mux data going from the register internal data bus. Default data is coming to the register from the internal data bus. Address buffer. This is the IR address bus, also called the tri-state bus. Reset hold halt when the bus is not in use. Tri-state, this is lower order data set data bus. This part in the processor, 16-bit register, is used to increment or decrement the contents of the program counter or stack pointer as part of the execution of instructions related to them. Yeah, coming to the flag registers, there are ALU includes 5 flag flip-flops, which are set or reset after an operation according to data condition of the result in the accumulator and other registers. They are called zero flag, carry flag, sign flag, parity flag, and auxiliary carry flag. Their bit position and flag register are shown in the figure. The microprocessor uses these flags to test the data conditions. This is the place where in D7 you have a sign flag, in D6 it is zero flag, D4 is auxiliary, D2 is parity, and carry flag is D0. Now, this sign flag, whenever the result of after addition or subtraction or any other operation, if the result is of positive, then it is sign flag will be set or reset. This one will be set or reset. Suppose if it is a negative number, it is a 0, and if it is positive number, it's will set as 1 in D7. So then in the coming to the 0 flag, then the D6 will be set or reset at 1 or 0. If the in the program any register contents are zeros, then 0 flag will set. Otherwise, it will reset. 0 flag will set, otherwise it will reset. Then auxiliary carry. In BCD addition or subtraction, if there exists a carry or a borrow, then auxiliary carry will exist at D4. Then coming to the D2, that is parity flag. The parity flag, which is when the number of in the result, after writing the program, in the result, the number of ones is even or odd. If it is even, the parity flag sets. If it is odd number of one, then parity flag resets. So it means it will be 0 when it is odd number of ones. And then this zero is a carry flag when in addition or in the subtraction. In addition, if the carry exists, or in subtraction, a borrow exists, then the carry flag sets. If there does not exist any carry or a borrow, then this zero will be zero. Next, this is the memory map. The total address of the 8085, starting address, it's here. This is a hexadecimal number. This hexadecimal number 000 is the starting address of the memory. So each hexadecimal number is equal to 4 binary bits. So that 4 into 4 is 16-bit address is mentioned here. So this is the starting address of the address bus, and one FFFF is the ending address of the memory. So the total memory is of 64 kilobytes of memory. So we can address. So the memory mapping. So some portion of the memory from starting point to some portion, then it is allocated by the manufacturer. Those who manufacture the microcomputer. So the starting address of the EEPROM and address is EEPROM. So the BAS program and whatever the program is written by the manufacturer is used 03FFH. So from 0000 to 03FF, this is the total memory utilized for the BAS program and monitor program, so that this will not be accessed to the programmer. And the other locations, let us say from 2000 onwards, after this there's some gap is there. Then from 2002, 13FF, 23FF, this is the memory that we can use for the EEPROM. From here, end address of the EEPROM and starting address of the 2002, 23FF. This is the ending address of the RAM. So this is where we can write some program from 2000 address location to 23FF address. So the total space we can use by the user's area. Whenever the power goes off, automatically it will be raised. Whereas the EEPROM, there is a permanently it will be written. So whenever we use the processor, this will be automatically stores, and it will not be raised at all. This is called the memory mapping. Now coming to the timing diagrams of the processor, how is a graphical representation. Uh, Presentation. It represents the execution time taken by each instruction in graphical format. The execution time is represented by T states, and the time required to execute the instruction, machine cycle, the time required to access the memory or input and output devices, and it is T states. The machine cycle and instruction cycle takes multiple clock periods. So each instruction, sometimes it may take 70 states, or sometimes it will be 10 states to execute each instruction. A portion of an operation carried out in one system clock period is called the T states. Yeah, this is one clock cycle, which is called one T state. From the this point to this point, one clock. One clock pulse is one T state, we call it as internal clock frequency F. So rising edge or positive edge. This is the falling edge of the clock. And then at this point to this point, the time taken is called T states, one time period. Has 7 basic message cycles. That is the upward fetch cycle, 4 T states to 6 days, T states it will take. And memory read is of these clock cycles to get the data to from the memory to the processor. It takes 3 T states or 3 clock cycles. And to write also similar time it takes 3 T states. And to read the from IO also takes 3 T states. And if you want to send or write data in the IO device also takes 3 T states. Interrupt acknowledge cycles, uh, which takes higher time than the above problem cycles, T states to 12 T states it takes. Then bus idle cycle. Yeah, this is per number of machine cycle, how much it is taking. It takes 4 upward fetches, 4 machine cycles. Memory read is 3, memory write 3, IO read 3, IO write this, so 3, interval 3. So these are the things that are to be shown while writing the timing diagram, how the address will be sent and data will be sent to the memory, and one address latch enable signal. This signal is to demultiplex the lower address and data bus, and read signal or write signal. Any one will be sent along with the either it is IO or M bar, which is if it is a memory, then memory read. If it is writing, then memory write. So this is the important things that is required in timing diagrams. Yes. This is the clock cycles 1, 2, 3, 4. 4 T states are shown here. This is the higher order address, and for 3 states, this is the lower address. When the lower address is sent to demultiplex, the address latch enable is uh, high. So during this is address is mentioned. After going down, the same lines are used for data bus. So data placed in the data bus, and then IO by MR. So the signal is high, then it will be IO device, and if it is low, then memory. So read bar is also low. So during this, whatever the data in the memory is placed in the data bus. So this 8-bit data places in the data bus and gets into the processor. So it's taking 3 T states, 1, 2, 3. So 3 T states, it is taking time to get the data from the uh, memory to the processor. The opcode fetch cycle fetches the instruction from the memory and delivers it to the instruction register of the microprocessor. Opcode fetch machine cycle consists of 4 T states. T1 state. During T1 state, the consists of the program counter are placed on the 16-bit address bus, and the higher order address, 8-bit address, higher order address 8 bits are transferred to a address bus of A8 to A15, and lower order of 8 bits are transferred to multiplex A address A to D, address and data, AD0 to AD7 bus. And this is the has to be high during this, so that it separates the address and data bus. The same thing is written in ports, which is discussed just now. During the beginning of this state, RD bar signal goes low to enable memory. It is during the state the selected memory location is placed in E0 to D7 of the address data multiplexed bus. T3 state. In the previous state, the code is placed in D0 to D7 of the A to D bus. In this state of the cycle, the opcode of the A to D bus is transferred to the instruction register of the microprocessor. Now, read bar goes high after this action and disables the memory from address and data bus. And the fourth cycle, the T4 state, the opcode fetch was fetched from the memory is recorded. This is similar one. Yeah, this is the memory write cycle. In a similar manner, the clock cycles, showing the clock cycles, three cycles, higher address, lower address, and at the same time, address slash enable is high so that during the first cycle, it will be sent to the lower address. Once the address is received by the processor and then ALE becomes low, then it will be acts as a data bus and the whatever the data brought from the processor, it will be placed in the uh, memory address, be specified by the address. So it places in the memory. So here IO by M bar is also active. So 001 is mentioned here. So this is writing the same similar way. This is taking one instruction, move A comma B. It means this is one instruction, it's assembly language program. So move A comma B means whatever is the data in like B register will be transferred to A register. And for this, the instruction code, the opcode will be 782. So what happens here? This happens only during the opcode fetch cycle. During the internal only it will happen. So there is no memory is required. So automatically transfer takes place within the processor. This is the data which is there in the memory 3 and 4, 5. So in this address location, it is stored as 3 and in this address location it is stored as 4, 5. What is 3 is there is some data which is to be stored in the accumulator A. And this is a 2-byte instruction. This 2-byte instruction is placed in the stored in the two address locations. One is A000, then A001. So the processor has to send this address first and get 3 and get to the into the memory to the processor, and the instruction register will decode it and then process it. Then next address as A001 is sent to the memory, and 45 is fetched from the memory and then places in the accumulator. So during this whole uh, time, it will be taking 70 states. So during the first 4 states, it is sending the it is getting the data from the first address location, and in the next address location it is taking 45 into the keeping in the accumulator. So whether it is read or write, so in the case both are in the reading, so reading from the memory. So fetching data from memory is nothing but reading data from the memory only. There is no place for write cycle. Next is another instruction. The load the LXI. This is the memory read and read cycle for a 3-byte instruction. This is a 2-byte instruction, which is first it stores memory, whatever the contents of memory will be placed in the accumulator, and then 7E will be placed in the whatever is the data in the memory will be placed in the accumulator. This is how the timing diagrams for corresponding to this instruction. This is for another instruction, and this is how an instruction will have STA instruction. Whatever is the address, this is the mnemonic, the assembly, right? Corresponding to this, we have opcode. So this is a 3-byte instruction. 41FF stores the STA opcode for STA, and then higher order address bus, higher order 8-bit number is 6A is stored into 4000, and then 52 higher order is 52. First lower order address and then higher address. This is the process that we have to store the address of the to be located. Whatever it means, there is some data in the accumulator to be stored in the address location 526A. So for this, what we have to do? STA 526A you have to mention. So this 32 is the opcode for STA, and then the address 526A mentions first is the lower address and then higher address. This is how you have to write it. 4 machine cycles for this particular instruction: opcode 4, memory read 4, memory read 3, memory read 3. This is again similarly type of the how much time it is taking for opcode for same thing. Opcode fetch, memory read, memory write. Fetching the opcode DBH from the memory is this, reading port address in CO. That is, this is a IO device, whatever is the data, uh, fetching from the IO device. You have to specify the location, address of this, and then we can get the data. 3 machine cycles which requires 10 these states. This instruction first is the DB is the 4125 is address. In this we store DB, which is nothing but in instruction, opcode for in section. Then the address of the port is C0. So there is some data to get the data from this particular address CO, so that it gets the information. Then send out data. So you can send the data from the accumulator to the output device. So it is instruction is called out instruction. So IO write you have to write. So this is the time taken for the particular instructions. Reading from the memory, it is taking so many T states, then sending right output port, IO port. This is corresponding to memory. And then from this onwards, it is responds to the IO device. So reading from the memory and sending out to the IO port from the accumulator to the port. So where is the port address? It is mentioned in the port address. Then fetching the opcode 06H from the memory. So move. This type of example also explained. There is data 2000 address. The data is 06 is stored, and in 2001 43 is stored. So what is the meaning of 06 is move immediately the contents of the B in the address to be stored in the B register. So 06 is move B with 8-bit data. What is the 8-bit data? This is the 43H is the 8-bit data. So once it sends the instructions and address bus and data bus, so that it gets the 06 from the memory, and then again in the next cycle 43 will be sent. This address is sent and this data will be placed in the data bus and gets into and stores in the B register. This is what it requires. This is the information for getting the data. First is it stores the upward fetches the first information, then this is the data gets into the and ports in the memory. And then it is of a similar one. And this timing and controlling the execution time taken by each instruction is a graphical format. The execution time is represented in T states, as we mentioned earlier also. The time required to execute an instruction is called instruction cycle. The time required to access the memory or input-output device is called machine cycle. And T states a machine cycle and instruction cycle takes multiple clock periods. So a portion of an operation carried out in one system clock period is called T states. This is falling edge and rising edge of the timing. Yeah, this is all discussed here. Right, it's repeating. Yeah, that's all for today. I'll stop here.